Hello, everyone. Welcome to another Kent seminar, you in person and everybody on Zoom. Today we have Professor Elefteriadou. She is the director of the University of Florida Transportation Institute. And she's the Barbara Goldsby Professor of Civil Engineering at the same university. Her research focuses traffic operations, traffic flow theory, and simulation. She received her master's in civil engineering from Auburn University and her doctorate in transportation planning and engineering from New York University. So please join me in welcoming Professor.
Thank you, appreciate the invite and a pleasure to be presenting to you today. I will talk about leveraging connected autonomous and connected and autonomous vehicles to transform highways, and feel free to interrupt if you have questions as I'm presenting today. Before we get started, one thing that I wanted to talk about is the University of Florida Transportation Institute. For those of you who may not be familiar with it, we're located in Gainesville, Florida. We have more than 140 faculty affiliates. We are very interdisciplinary, working with many different colleges. This year we have had 12 million in research expenditures. We have about 40 staff and about 50 students. You may be familiar with the McTrans Center. It's housed here. We also have a technology transfer center, and we lead the University Transportation Center for the Southeast called STRIDE, along with another 10 universities in the Southeast, and our theme or focus is on congestion mitigation. One of the initiatives that we've been working on over the last 6 or 7 years is the I-Street Living Lab, which is, and I'm showing here how to access the website. It is a real world test bed, actually living lab, because it's on actual city streets around Gainesville, around the campus. We're collecting a lot of information, a lot of data. We have 130 roadside units. It's a collaboration between FDOT and the city of Gainesville, and so we're working very closely with our partners. We have 60 vehicles that are instrumented and are receiving connectivity information. Those vehicles belong to UF Fleet, but also City of Gainesville and FDOT. And we have about 25 projects that either have been completed or are ongoing, related to different aspects of advanced technology. So the main objective with I-Street is to improve mobility and safety. And so our projects relate to applications of connectivity, applications for autonomy, advanced signal control, and other traffic management and safety topics. Some more information here about I-Street, and one is one of our projects has been an autonomous shuttle, which had been operating on in the downtown area. The project just completed in September, so we've been able to do some evaluations, both from a traveler perspective, but also from a traffic management perspective, and the way that the autonomous vehicle operates within city streets, and how other vehicles, but also pedestrians and bicycles react to it. And in terms of data, we are collecting data from several locations around the state, including around Gainesville, I-75 in Gainesville, the I-4 corridor between Tampa and Orlando, and also down in the south around the Keys area. So that brings me to one of the major initiatives we've had, initially with funding from the National Science Foundation, but then with additional funding from FDOT, and with support from not only FDOT, but the city of Gainesville and a couple of industry partners, Econolite and ISS. So the question that we are aiming to answer is how can we use autonomous connected vehicles to reduce congestion? That's a question that's been, you see a lot out in the press, but also in the literature. So we set out to develop a system with which we can actually improve congestion. And the system is what you're seeing here on your screen, is collecting information from vehicles, including conventional, connected, and autonomous, but then developing a system where we are optimizing the signal control and vehicle trajectories jointly. And so with that, we're treating autonomous vehicles as robots and providing them instructions about how to move, but at the same time optimizing signal control. So the system I'm going to talk about collects data through DSRC, through radar, through video, and looks at what's the location of conventional vehicles, first of all, because we have no other way of knowing it other than through sensors. For connected vehicles and autonomous vehicles, we have the ability to get through basic safety message information, or an adjusted basic safety message information about their location, their speed, and more detailed information about their direction and destination. So the information that we're collecting in the field goes through a sensor fusion system. We call it Sensible. And that feeds into our algorithm. Then our algorithm comes up with optimal signal timings and also optimal trajectories for autonomous vehicles, which the autonomous vehicles are able to follow those trajectories, but also recommendations for connected vehicles and potentially conventional vehicles through an app. So I'm going to talk about this system, which has had several different iterations, but here just to give you a sense of what we're trying to accomplish, and I hope you can see my cursor here. The vertical axis here is showing distance, horizontal axis is showing time. So when we are through our sensor fusion system, we are detecting the vehicles arriving at time t1, and we are able to then develop optimal trajectories and project that to the time where those vehicles will depart. So by being able to do that, we can minimize the number of stops, and we can have vehicles travel through the green. So the process, like I said, optimizes signal control together with the trajectories of vehicles. And this particular one is showing 100% autonomous vehicles. The system is looking through a certain horizon where you're collecting the data, you're projecting what the signal control will be in the future, and then continue on to the next time interval. One of the complications that we had to work through is we have to know the destination of the vehicle. And so it's important to have that in the basic safety message, because the destination also defines the way the trajectory has to be plotted. So the speed that it's going to be able to maintain going through the intersection and traveling to its destination. The graphs that I'm showing here are from simulation. One of our first simulations was looking at a simple four-way intersection. And so we're looking at 100% autonomous vehicles, which is the simplest case, and looking at comparing what happens when we use our system versus actuated control. And depending on the scenario, we can have delay reduced by anywhere from 16 to 79%, which is quite significant. As you're seeing here in the top left graph, you see the average travel time delay on the vertical axis, and the horizontal is showing the demand. And so for lower demands, there's not much of a difference. We don't have significant savings. Most of the savings happen at the higher levels of demand. Then the throughput, very similar. Again, we have most savings for in terms of throughput happen with higher demands. Now we did that, like I said, 100% autonomous vehicles in simulation, but then as part of our NSF contract, we had what's called the transition to practice. And so we developed a system to do this actually in the field. And so this is the site we did our first set of testing. It's at the Florida Department of Transportation Traffic Engineering and Research Lab. They have a facility with 2 signalized intersections. So we brought our vehicles, our signal controller, computers, and so on, and tested the system at this intersection. One of the lessons from field testing, which is quite different from simulation, in simulation, you can create the vehicle arrivals in advance and kind of develop your algorithm the way that you want it to operate. But in the real world, you don't know the rate at which vehicles will arrive. So if you can see the graph there at the top right, we remember we have our horizon here, and if we use a certain amount of time, whatever that would be, let's say 20 seconds as a horizon. In those 20 seconds, the first vehicle has already traveled quite a bit of a distance, and that distance depends on what the speed of the facility is. And so depending on, first of all, what the communication range is, what that horizon is that we're using for optimization, we may or may not be able to optimize now the vehicle's path anymore. So we developed a graph here at the bottom right, which kind of correlates the speed to the communication range to the horizon that we're using, because there are some combinations of these that are just simply not feasible. So one of this is just showing the algorithm that we ended up developing. We call it RIO, Real-Time Intersection Optimizer. We've done more with field testing, not just in a closed course environment, but we've been doing some more experiments out in the real world. And for example, at the bottom right here, I'm gonna run this here so you can see, we have the dots here represent the optimized trajectory, and the solid line represents what the vehicle is actually doing. And so we're able to look at what the guidance that we're providing to vehicles versus what it is that they're actually doing. I'm going to show you a little bit what the types of sensors that we've been using, video and radar. We've used LiDAR also, because one of the additions that we've made is to detect pedestrians. The intersection I showed you earlier is on the UF campus, and there's a lot of pedestrian traffic there. And the DSRC unit, which actually we're having to replace that to CV2X type equipment. Again, here is the video just showing this is the intersection we have instrumented. It's outside the civil engineering building in Gainesville. The football stadium's here on your left. And so the intersection has now a set of sensors that we're looking at, and we've done experiments for vehicle trajectories. I also want to show you part of the project. We developed an app that any vehicle, even conventional vehicles would be able to use. And so what you're going to see here in the video is as the car approaches the intersection, and this video is actually taken at the Turl, so it's a closed course facility, not an intersection with regular traffic. It's starting to provide some guidance to the driver. Now, we didn't have drivers outside our researchers, and so the app is very, very crude. We weren't aiming to do a human factors project. I think this would be a very interesting extension to check and see what type of information a driver would want to see and how they would use it depending on the circumstances. But we wanted to see how feasible it would be for a driver, one of our researchers, to follow the recommended trajectory. So we experimented with optimal speed, so a speed recommendation. We experimented a little bit with time to green and things like that. And then we also compared different types of trajectories based on the fused information. We did several different experiments with what would make most sense in terms of the type of data that are being included into the sensible. The other component we've been working on is a simulation platform. And so we have connected Rio to VISIM, and that allows us to do more extended experiments with conventional vehicles using VISIM's logic rather than us having to rebuild all the car following, lane changing, and all that. So the platform is working right now. We actually have a paper to be presented at the WSC in Singapore in December this year. So this was not trivial. We thought it was going to be easier than it was, but in the end, it works. Another extension we're working on right now, we just published a paper on that, is the extension to arterials. That becomes a little bit more complex because of the offset between the two intersections and coordinating with the side streets as well between the two intersections. We published a paper on that last TRB. Another application we've worked on, and we have a couple of publications on, is the trajectory optimization for roundabouts. So in this case, we have the paper just dealt with a simulated roundabout. So you have vehicles being detected where that outside circle is. Then within this zone, there's adjustments between the large circle and the smaller circle, adjustments based on the anticipated vehicles within the circulatory traffic stream, and then the execution within that smaller circle. And this can also save quite significantly in terms of travel time. Now, for this one, the experiments we've done, the simulation experiments we've done are 100% autonomous connected vehicles. I just want to show another set of research papers deals with a similar issue, but for freeways. And so over here, I'm going to show you the bottom is showing conventional vehicles. The top is showing autonomous vehicles, same level of traffic. And so, of course, with the conventional vehicles, traffic tends to congregate to the right. What we're doing with the autonomous vehicles is, and this is 100% autonomous, is pushing vehicles toward the left. And so you have many more gaps and much more productive, if you will, freeway, because otherwise, if you rely on human drivers, and of course, depending on what happens downstream and what happens upstream, you don't have as much, you don't have good utilization of the freeway. This was work by, we published it, Clark Letter was one of my PhD students, and we're doing some extensions. We've done an extension to weaving, and we're doing and this was primarily for merging. So where are we next is we're expanding our simulation experiments. We are working on improved sensor fusion and sensor capabilities, telecommunication. This is one of the issues that, one of the main reasons that the system is having a hard time is the accuracy of the sensing. The simulation can work well. It seems that we do have improvements in travel time and throughput, even with a mix of autonomous and connected vehicles for the applications we've tested. We plan to do some more experiments with the mobile app, and especially the interface and the type of information that drivers may react to more effectively. And lastly, the computational efficiency. There's a lot of work that we're doing to make sure that the processing is faster, because one of the things that that happens in our applications is when we consider combined autonomous and conventional vehicles, you have to take into account that conventional vehicles may not do exactly what you want them to do. And so we can't just rely on having an optimal trajectory given to the vehicles. You have to go back and see, well, have all the vehicles done what you expected them to do? And if not, what needs to be readjusted? And so part of the optimization and part of the computer modeling has to do with what is it that we have to re-optimize, and what is it that we can just live as is. And so creating that is, making it faster computation so that it can work for the network. And I want to acknowledge the PhD students who have worked on this, the sponsors, NSF, FDOT, and USDOT, Stride, our UTC. Our industry partners, Econolite with the signal controller, Siemens and Unix have helped with instrumentation, and Brand Motion with vehicle interface, with vehicle instrumentation as well. And faculty and staff, I've served as the PI for these projects, but we've had collaborators from computer science, Dr. Sanjay Ranka, and he and his students work mostly on the sensible side, the sensor fusion. And Dr. Carl Crane is the faculty member working on autonomous vehicles. Dr. Prithvi Manjunatha is the iStreet manager, helping with all kinds of things related to iStreet. So with that, I'm gonna turn it over back to you for any questions.
Do we have any question in the room? Check the chat. Okay. Professor, I had a question about the equipment you showed on one of the slides, specifically about LiDAR. What is LiDAR helping with that you cannot do with a regular camera?
So we were doing some experiments with LiDAR to be able to detect pedestrians. We had a LiDAR that was looking at the level of the street level to be able to detect whether there's a pedestrian there at the corner. It's giving I guess a little bit better information in terms of trajectories and locations of other objects within the screen. The video cameras we have is focused extensively on the vehicles. I'm not sure if could you accomplish something similar with a video? Probably. It just it was part of the experimenting to see what LiDAR was able to provide us in terms of pedestrian movement, and the city has been experimenting with LiDAR as well.
Okay. Thank you. Do we have any other questions from the room? Please go ahead.
Hi, Professor. Thank you for the presentation. It's just for curiosity. When you mentioned about the the simulation for fully conventional vehicles, I was just wondering because when the vehicles are approaching the merging lane, sometimes they may try to like be more gentle and move to the left lane. So is that considered in the simulation, like how maybe drivers will proactively go to the left to move to the left lane to allow the other vehicles that are approaching to get into the roadway?
Yeah, certainly that happens. It depends on the simulator. Different simulators do it differently. There are different assumptions. The one that I showed you is, I believe it was Corsim, but we've also been using more recently. We're using Visim in the loop with the signalization. So yeah, I mean, you can certainly test different options with the movement of the vehicles. What the conventional traffic is not going to be able to do is to follow guidelines in terms of you need to be there at this location at this time with this maximum speed. If people are left to their own devices, they don't have the big picture, if you will, of how to make the bottleneck, whatever bottleneck it is, operate more efficiently. And even if some vehicles do what you're saying and they move to the left, they're doing it for their own purposes. They're not doing it to optimize the overall system. So it still wouldn't be the same. Does that answer your question?
Yep.
We have another question here in the room.
Yes, for the mobile app, it was showing 3 numbers on the interface. I was wondering what numbers exactly represent.
One was the optimal speed, the other was the time to green, and the other was the time left for red. So we were trying to see what information that the driver would be easier to follow. And this was just, it was not an extensive study with different subjects. It was just within our research team, what works so that we can make our experiments work. So it was a very crude app just to run through the experiments.
Thank you.
We have another question here in the room.
Thank you for the presentation, Professor. I was wondering, heading into the future, in terms of deploying these technologies, do you think that new systems have to be developed from the ground up to accommodate for these technologies, or do you think they're going to be embedded as features into existing navigation systems like Apple Maps or Google Maps? Because I think a lot of the groundwork has already been laid for that. So how do you see this being deployed in the future?
Yeah, that's a good question. With the experiments that we've been doing, not just related to this research, but with iStreet, we had several drivers using, a connectivity app. And what they were saying is, yeah, this is great. I like it. Could you integrate it with a navigation app? So I think drivers really would appreciate consolidation to the degree possible. They don't want to have 15 different apps, one for monitoring pedestrians, another for monitoring signal control, another for navigation. They want to have one app for everything. And that requires some more work from vendors to make that more palatable.
Just a small follow-up on that. Do you have any idea if any of the big tech companies like Google or Apple have shown interest in this research, or maybe they want to like sponsor it or get a hold of the algorithm so that they can try to implement it at some point? It's just out of curiosity.
Yeah, we have several different collaborators, and we have also we have plans to license the software. We already have it protected, I guess, for within UF. So this is definitely one of the next steps.
Thank you.
Sure.
We have a question for Professor Kadi here in the room. Yeah, she can
Oh,
hear
I
you.
couldn't hear you. Thanks, Lily, for being with us. We really appreciate your presentation. I have a quick question. What does it take in order to convert the system that you have for wildlife detection, especially when people are driving and there's animals keep jumping in? So that's a completely different than pedestrian. What does it take to do something like this?
Sorry, I didn't hear you. To convert what?
Oh, I was, okay, can you hear me well now?
Yeah.
Okay, now it's good. Thank you. I was saying that this is really interesting, but one of the concerns that I was reading about recently is the detection of wild animals during the driving. And what does it take to convert a system like yours from pedestrian to detecting like deers and so on during the driving?
That is, this is not my area of expertise, but I've learned a little bit over the last several years. It's hard even to go from, let's say, using LiDAR for pedestrians to using LiDAR for bicyclists. So I'm sure it's going to be difficult to use it for detecting wildlife, because the point cloud that is that the pedestrian generates versus what a bicyclist generates versus what an animal generates are very different. And the other thing we've learned is that there are databases out there kind of to compare between different types of algorithms, either for video or for LiDAR. But they are very simple from what I've seen. So there's a lot of work that still needs to be done to be able to accurately and quickly detect whether it's pedestrian or animal or scooter or bicyclist.